Good afternoon. Hello, everyone. Thank you for joining us today. It's nice to see we've got a great turnout here in the room with us, and I would like to welcome everyone that's joining us remotely as well. This is session C4A, New Developments in Connection Design. This will be presented by Bo Doswell. I'll let Bo cover the PDHs later. My name is Jules Vandepas. I'm with Computerized Structural Design Structural Engineers. I'll be moderating today's presentation. I've got a couple of quick announcements and then we'll get right to it. To obtain the PDHs, you will need to visit www.aisc.org/NASCC-PDH. You can do this from your phone or mobile device, from any computer, or from the station set up at level 300 in the convention center. For this presentation, Bo will take questions at the end of the presentation. If you're in the room with us, just raise your hand at the end and Bo will call on you as he can. For those of you who are joining us remotely, you'll find instructions for submitting questions included on the viewing page. And we'll address questions as time allows. We might not get to all the questions, but we'll do our best to address everything that comes up. By we, I mean Bo. And so now to give you today's speaker, Bo Doswell has been in the steel industry since 1985, first as a detailer, then as an engineer. He has a PhD and is a PE. He's a principal with ARC International. And due to the really fine work Bo has done, he's become one of AISC's go-to guys for research and expert advice on connection design. So, Bo?
Thanks, Jules. All right, so if you've been to the conference in the last 3 or 4 years, you'll notice that this new developments in connection design topic has been repeated. This will be the third time we've given it. And I believe it was the very first year where we did the strength of rectangular connection elements. We talked about strength and stability of connection elements. And the following year we did, at least my part of it, was on a new method to design gusset plates using notional loads. And this time we're going to kind of go back to that connection element thing, but this time we're going to use the connection elements and design coat beams. We talked about that a little bit a few years ago, but this time there are a few things that are different. First of all, we're going to concentrate exclusively on coat beams. And second of all, the information that we talked about previously is now in the AISC manual, in the latest edition that came out. So before we turn the page, let me give you the PDH code one more time. It's, just in case you want to sneak out early, it's 42683. Here's what we're talking about on the coat beams, and I think everybody probably knows what a coat beam is, but I'll go ahead and show you anyway. The figure on the left is from a high-rise structure in Chicago. While I was working in Chicago for AISC several years, maybe 8, 9 years ago now, we got a chance to go up and take a look at this building under construction, and that's when I took this picture. It looks like a pretty typical single coat beam because it's coated at the top flange only, with the exception that if you look really closely, you'll be able to see on the other side of the beam there's a joist seat. So it raises that top of steel of the supported beam, of the coat beam, 2.5 inches from the supporting beam. And on the right-hand side, you see a galvanized double coat beam, and that will typically happen when you have two beams that are of equal nominal depth framing to one another, where you have to coat the top and the bottom flange. And that's a picture that I actually took about 2 weeks ago on a site of a industrial plant. So in those figures that I just showed you, those are pretty typical cope lengths and fairly typical cope depths. The one on the left was a little deeper, 2.5 inches deeper than you would normally get. But a lot of times in practice, you're going to end up with longer and deeper copes than just your standard cope. And once you get into that, you can end up with some things like buckling problems, buckling of the cope, that we'll talk about more in just a minute. So what would cause the cope length to increase? Well, here's one example. This is not an extreme example. That's coming up on the next slide. But this is just a beam plan view on the left side there, the W18 at 55 skewed beam framing to the W24, which means you're going to, if it's top of steel is equal for both of those, you'll have a single coat beam. But the problem is that it's skewed, so it's going to, that 45 degrees is going to cause an increase of about 40% on your cope length. In this case, from the center of the W24 to the face of the cope is 11 inches. So you can see with just a 45-degree skew, we've increased our cope significantly. And that's a pretty common connection. In fact, I just did one similar. This one and the next slide are both from a 2005 presentation I did, and they're both based on actual projects I was working on in the previous years. But I actually did another one just real similar to this, bend support structure, in the last month or two. So you got pretty big loads on those, so you end up with the end plate type connections like that, rather than a single-sided, maybe a bent plate connection. Now this next one may look extreme to you, but we run into that sometimes. I remember this is not the exact connection, but this is similar to a connection that we had on a performing arts center, maybe back a couple of decades ago when I put this presentation together. And you can see, due to the tight skew, the plan view is on the left, and then when you flip down, you can see the elevation view of the W16 here. So you've got a W16 at 26, which first of all, it has a thin web. I believe it's right around 1/4 of an inch. And then due to this tight skew, you end up with roughly a 20-inch cope to the work point over here, from the work point to the face of the cope. And then you're framing to a member that's of the same nominal depth, so you end up with a double cope. So all of these things put together means that you're going to fail in buckling rather than yielding on this beam, on this cope. Now, while I'm at it, this isn't part of the presentation. While I'm at it, designing the connections is what we'll talk about in this presentation, but there's also another thing to watch out for this type of member, and that's the lateral torsional buckling of that W16. If you're the engineer of record and you're subbing the connections out, that doesn't really help you in your lateral torsional buckling calculation. You've got to know that if this beam's not braced, or if it is braced before the bracing gets in place, that the lateral torsional buckling strength of this beam is going to be greatly reduced. And you can contact me if you want information on that. One of the references is the research that was done that I'll tell you about later. It's a report by Ching-Yura and Johnson at University of Texas, where they did a lot of development of equations for the lateral torsional buckling of the cope beams, and they also did a lot of work on the cope strength, which is what we're going to be talking about. So the presentation, the first half will be single coat beams, and then we'll talk about double coat beams. It'll be split roughly in half. We're going to cover the same things in both parts. We're going to have one slide on shear strength for each one, and that's because it's well defined in the specification. We don't really need anything else. Then we'll move on to the flexural strength. That's where most of our time is going to be spent for single and double coat beams. That's for single coat beams. flexural strength is going to be in the manual. And then we'll move on to some things that are not in the manual or the specification, and that's the axial strength. And if you have axial loads in combination with your shear load, you need to know how to combine those. And we'll talk a good bit about this too, because it's primarily, most of my presentations, I'll say the word judgment at least 10 times. And that's what this is all based on. We'll try to go over the background of those first two items in both cases, the shear strength and flexural strength, or at least the flexural. The shear is kind of pretty straightforward. But once we go over the background of that flexural strength, then it's up to you as an engineer to use your judgment and what you know about how this beam is going to behave, how this cope is going to behave, to come up with your design method for the axial strength of this cope. So that's what we're going to do. And when we get to this axial strength part, you'll see how I've done it, and I want to go through how I've done it, and then that will allow you to decide if you like that method or not. I'm not going to get upset if you don't use the method that I'm going to give you up here. I want you to use your own method, the method you're comfortable with. But hopefully we'll get enough background information where you can go through and decide how to do it. And then we're going to do the same thing for double copes. We're going to go over the shear strength, flexural strength, axial strength, and combined loads. Now, this is a pretty good timing for this discussion, because what we ended up with, going from 14th edition to 15th edition, is a revised design procedure for both single and double coat beams. And it's been a long time coming on this, because I can remember even, 7, 8, 9, maybe even longer than that, years ago, trying to figure out how to go from this Ching, Ura, and Johnson report, which was all done in ASD, allowable stress design. It was done before the Green Book, the 9th edition manual, and I believe it was the 89 specification. So back then we were allowable stress design, and we were trying to do things with the elastic strengths, the section modulus of beams, and some things like that. But in reality, even if you look back then, we were really designing for the plastic strength of if you just look in the flexural strength of a beam, we were really designing for the plastic strength by giving it a 0.66 instead of a 0.6. So things like that, we were kind of doing a fake inelastic design even back in the Green Book. So these cope design procedures were kind of lagging behind everything, especially the connections, because in the 14th edition manual, we had everything, at least as far as I know, we had everything converted from all this allowable stress information we had to a strength design procedure. Somewhere between that first LRFD and this 14th edition manual, we had figured out a way to convert everything, but we couldn't figure it out on these copes. So finally, after all these years, between 14th edition and 15th edition, we were able to do that. So now you're able to take account of the inelastic strength potential that can potentially be available, that is available in most copes. One other thing we did while we were at it is we eliminated the limits of applicability. If you look back in the University of Texas report and in all of the AISC publications, including the 14th edition manual, there were limits on the cope geometry. For example, the single cope beams were limited to a cope depth of, I believe, half the member depth. And then the cope length was limited to twice the member depth. And for double cope beams, you had the same length limitation, but the cope depth was limited to 20% of the member depth. All right, so we took those limits out, and I'll show you how we did that. It turned out to be pretty simple. We just put limits on our equations as we went along, and I'll show you how we did it. One other thing we did with, I'll show you the finite element models that Robert White and I did. Robert's right down here. I was hoping that he would come up and give the presentation for me, but we did some finite element modeling, and for the double coat beams, found a way to use different coat sizes at the top and bottom, as to where previously we were limited to, well, at least it was implied, the equations that were given to us implied that you had to use the same coat size at the top and the bottom. And as we know, sometimes you run into cases like I've got on the screen where your coat length may be different at the top and the bottom. Same thing with coat depth. So we wanted to eliminate those restrictions on the equations. So in the presentation, like I said, we're going to do single coat and double coat. We're going to go over the latest design techniques in the manual, in the 15th edition manual. We're going to hit the background, and I've already explained why I think it's important to do the background of these equations. And then we'll use that background to go in and try and figure out how to do axially loaded copes. So let's get moving on the first half of the presentation, the single coat beams. We'll start off with the shear strength. It's straight out of the specification. You'll see an identical slide once we get to the double coat beams, spec section J4.2. Now, chapter J is going to be for connection design. But J4.2 goes into the yielding of connection elements. So what we're going to have as a nominal strength is 60%, that 0.6 is the von Mises shear factor, times the yield stress, F sub y, times the gross shear area, A sub GV, which is H sub O. H sub O is the remaining depth at the coat section. So we're looking at this cross section here, with the remaining depth of H sub O. So it's going to be H sub O times T sub W to get A sub GV. All right, so there's not really much to talk about on that. That's straight out of the specification. But once we get to the flexural strength, now we're getting into the manual. And what we're going to do, we're going to talk about the background first, and then we'll talk about what's in the manual. So we're going to repeat some of the equations with maybe slightly different terminology within those equations. But right now, we're going to say that we're dealing with a frictionless pin as an end connection, and that is going to be right here at the end of our beam, right where this R is applied. We're saying that R is applied at the face of the supporting member for now. And that's given by the definition, and the picture shows E up there to the face of the cope, from the face of the supporting member to the face of the cope. So we can calculate a moment. We know we've got a shear in there. We can calculate a moment, R times E. And the way we do that, I think it's pretty clear, but I mean, this kind of goes back to almost everything that you do in connection design that's not in the manual. You know, if you've got an equation in the manual, just go to the manual and apply the equation. But in most cases, for a connection, you're going to run into things where you have to figure out how to do it. All right, so if you didn't have any equations at all and you wanted to design a coat beam, well, the first thing that I would do is kind of cut it right there and throw away everything on the right. Say that that's a fixed end of a cantilever beam. In other words, we've got a cantilever beam spanning from here to here. Everything from here over is cut off. We have a fixed end here, a pin here, and a cantilever beam length E, so you get your moment equal to R times E. But once we do that, that's pretty basic, and I've got the elastic stresses shown on there. Of course, that's not really what it looks like. If you look at the measured stresses from tests or finite element models, and we'll need this information later. It kind of comes in like this at a curve and then peaks out here. It may be 50% or 70% higher than what we calculate with MC over I. Okay, so we've got a cantilever beam model, and if we want to design that for buckling, we're going to go in and call this a local buckling problem, and this is not my idea. This is straight out of the University of Texas report. They said, we're going to design using a local buckling model for single coat beams, and all we've done here, at least for this part of it, is kind of rearrange what we had before. So what we're going to do, since the new specifications call the slenderness lambda, you know, if you look in chapter B, we've got our slenderness of, say, a column flange. It's going to, you know, B over T. It's going to be defined as H sub O over T sub W, where, of course, H sub O we've already defined as the remaining depth at the cope. Okay, so that makes sense because if you look in chapter F, that's how we define the slenderness for WT members. And that's really what this is if we're calling this a short cantilever. It's a WT member with the stem and compression with the stabilizing effect of this cope. It would be a WT member if that cope was infinitely long. Now that we know we're going to design as a local buckling problem, we can go into specification chapter F for the WTs and take a look at what they have. It's a three-part curve, depending on what your slenderness is. And, of course, you got your plastic strength up here, your linear transition range here, and your elastic portion of the curve here. This is the slenderness along this axis, and M over MP, the moment divided by the plastic moment on the vertical. And I think everybody's pretty familiar with how to design beams, but so I'll go through this fairly quickly. When we're in the plastic range, we get to use the yield strength times the plastic modulus. In the manual, it's called Z net, and that's the plastic modulus at the cope. When we're in this linear transition range, or the inelastic range, we see this equation in the specification, and we've got the plastic moment M sub P, and we've got the yield moment, or at least theoretically, if it had no residual stresses, it would yield at the yield strength times the section modulus at the cope. And then you've got, in the brackets there, you've got lambda sub P, and lambda sub R. So that's straight out of the specification, but we need to figure out what to do with it if we're going to put this in for cope buckling. We know what lambda is, we know what M sub Y is, and we know what M sub P is. We really just need to define lambda sub R and lambda sub P at this point. Now, I have to give the credit for this idea to Tom Murray from a manuals committee meeting. And we were looking at the data, and as it turns out, you know, what we did is, first of all, we took an approach that's very similar to what is done to develop the, if you look in chapter B, you've got the tables for, say, a compression member, and you've got lambda, whatever that's defined as for local buckling, and then you've got lambda sub R and lambda sub P. Your lambda sub R, well, lambda sub P is typically defined using experimental results. Lambda sub R, you can define using some theoretical results, plate buckling equations with like a fudge factor in there to account for residual stresses and out of straightnesses and things like that is typically what we do for those. So we went through the same procedure for these numbers. And it just so happens that lambda sub P was equal to lambda sub R over 2 based on the experimental results. So Tom Murray said, why don't we just simplify the equation, get rid of lambda sub R altogether, use lambda sub P, we don't even have to calculate lambda sub R anymore, and substitute lambda sub R equals 2 lambda sub P into the spec equation, and we end up with this slightly simplified equation that I've got shown for the linear transition inelastic region. Now, once we get into the elastic region, now you're going to be primarily inelastic or elastic. You'll probably be in this range right here, or maybe up here. Rarely will you be in the plastic range up here on the single copes. The reason is because they're so deep. That H sub O dimension is so deep that it's hard to get the plastic strength. Now, I'm not saying never. I mean, if you have a jumbo shape that's coped on one flange, 3-inch thick web or something like that, then sure, you will probably end up getting the plastic strength out of that. But for a W16 at 26, you'd have to have some pretty small cope dimensions to get the plastic strength out of that one. When we're in the elastic range, the answer you get, the equations aren't necessarily the same as what we had in the 14th edition, but the 15th edition and the 14th edition answers that you get will be the same. And that's only in the elastic range. So let's go in and take a look at what those guys at University of Texas, the Chingura and Johnson research showed, and how they developed the equations. Because we're going to reuse those equations. We're not going to reinvent something that's already working for us. We're just trying to, we want that part, the elastic part, to be the same, because it was already reasonably accurate. So what happened, and if you look in that report, what they did is H sub O, your stress distribution theoretically is going to look like this, where you've got your neutral axis here. So if you chop it off there and kind of move that point down here, we've got a solution for this plate buckling problem. We don't have a solution for that, not even close. So what they did is they said, well, we know what the solution for this is. Let's try to model this as this by setting H sub O equals to B and a few other things. Well, on that top equation, the sigma critical equation, that's the critical stress, a theoretical plate buckling stress. And you can look in Timoshenko or any of the plate buckling books or the SSRC guide or anything like that, and you'll see this equation. It's dependent on the plate thickness and that width B, and it assumes an infinite, most of the equations assume an infinite distance here, an infinite length. We know that's not true for our copes, so we need to make some adjustments here. But the first thing we do, we'll plug in Poisson's ratio and pi, and then we said B is going to be equal to HO, and T is equal to the web thickness. So we're going to plug those values in. As it turns out, T over B is equal to 1 over lambda, so we'll plug in lambda down here. So this is a good equation that we can go with. K sub E is the plate buckling coefficient, which theoretically is 1.61 for this condition. But we're not going to, we can't use that here because we've got a lot of complications. This doesn't look like a coped beam. So if you want to call F a fudge factor, officially it's called a buckling adjustment factor, and it accounts for everything that the plate buckling coefficient doesn't account for. So, and it's going to be empirical, and it's the same as what we had before. F is in your manual, the 14th edition manual. We're just going to use it in 15th edition the same way. Now, here's one thing we did. This is kind of what we did in the 14th edition manual, this part. We added this 1.61 so that we no longer were constrained by the cope limits. In other words, we no longer have to use a cope length of twice the cope depth, or smaller than that. Okay, so our F, the buckling adjustment factor or the fudge factor, takes account of all these things. Stress concentrations, okay, we talked about that. The stress concentrations are going to be higher, so that's going to lower your buckling strength. Moment gradient, as we know, the moment's going to be 0 here, theoretically, maximum here, so this stress is going to build up as we go along that length C. All right, so that's a beneficial effect. The shear stresses are going to be a degrading effect to this. The plate buckling calculation that we just put up there, that sigma critical, doesn't account for shear stresses. All right, and there's a couple of other things. For example, the plate buckling model has a rigid out-of-plane restraint along this line, and we don't have that here. That can, in fact, if you look at, if you're interested in these things, I would look at that University of Texas report. You can download it for free from the Ferguson lab there. If you look at that, if you look at the buckle shapes, some of these were curved. They buckled here, and they curved all the way in to over here, this far into the web. So obviously, we don't have lateral restraint at that location. So really, as we said earlier, we only need lambda sub r and lambda sub p now. And we know the ratio between lambda sub r and lambda sub p is 2, so we only have to solve for lambda sub r. And this slide shows you how that was done. The first step is easy. All we did was plug that k sub 1 from the last slide with the fudge factor in there for k sub e, the theoretical plate buckling coefficient, plug it in here, and you end up with this equation. And then, similar to what we do for all of the local buckling lambda sub r's in the manual, we substituted sigma critical, f sub y for sigma critical, and then sigma r, or lambda sub r for lambda, and solve for lambda r, and here it is. It's just the 0.950, and then you've got e and f sub y under the radical, just like you do a normal local buckling equation. Some constant out here. The difference is that we had this k sub 1 factor under the radical, and that accounts for the cope length. So that's a stabilizing effect due to the cope. And we said that we're not going to use lambda sub r in the design procedure, so we go ahead and divide by 2 to get lambda sub p, and there you have it. That's how the manual equations were derived. Now we can move on, and we'll go through this pretty quick because we've already gone through everything. Here's our equation in the manual. One thing I'll point out here is that I've got a subscript. This is the LRFD version. The subscript U to indicate the ultimate strength or a factored load. So your factored in reaction times the eccentricity E equals the moment. But the main thing that I really wanted to point out on this, okay, you notice everything up to this point is the same as I had on that background slide, but then it says, unless a lower value for E can be justified. In other words, it's giving you an out if you want to try to lower the moment on that cope. So you can, and the reason is because that's not a perfect pin. That inflection point, well, when you first load that up, depending on what type of connection you have, if you look at especially some of those old shear tab tests, it might be 1.5 feet out here toward the middle of the beam. And then as you start loading, it kind of incrementally moves in as things start to yield, even a tiny bit of yielding around the bolts. And then it finally moves in fairly close to the support. So the reason I'm telling you this is I haven't really found an accurate way to use that unless a lower value can be justified part of this yet. I looked at some of the test results for both these and for the double coat beams and tried to match it up with the inflection points, because some of the inflection points were reported in the tests. And I really couldn't, in some cases it was unconservative. I think some more time needs to be put into that, but if you can figure out a way to do it, then it gives you a way to do it in the manual. All right, we've seen this before. This is the lambda sub p we derived. This is straight out of the manual, limiting slenderness for a compact web. And then you've got the 1.61 factor on our k sub 1. And this part is straight out of the 14th edition manual, so it's copied straight over. Actually, it's out of that Texas report, and I think it originally got put into, does anybody remember that Volume 2 Connections Manual, that green and blue book? Yeah, that one, I believe, I could be wrong, but I think that's the first time this was used in an AIC publication, and it's made it all the way from that 9th edition, half green book, half ASD, half LRFD book, all the way to the 14th edition, and now it's made it into the 15th edition too, because we're still using this because it's the elastic buckling of that cope. And it's the same thing here. The what I'm calling the fudge factor, the buckling adjustment factor, it's the same as what we had before. We did make one minor change. You know, you can see that it's just dependent on the range. Your buckling adjustment factor is just dependent on the cope length divided by the member depth. We did add this part, less than or equal to 3 when you're in that range. And once again, that's so that we have no limits on the cope geometry. So when you go into the manual, you'll see these 3 parts of the local buckling curve. And of course, basically it just tells you to use plastic moment when your lambda is less than lambda sub p. And notice here, instead of lambda being between lambda sub p and lambda sub r, we replaced lambda sub r with 2 times lambda sub p to save you that 10 seconds of calculating lambda sub r. And here's the equation that I showed you that's based on the spec equation, but it's got this simplified part in the brackets over there. And then once you get to the elastic region, like I say, this looks different from what we had in the 14th edition manual, but the answer is the same. Here's our equation that we derived earlier, the sigma critical equation, and we're calling it F critical just to match up with the terminology and the specification. It's going to be F critical times the section modulus at the cope. So this is always the fun part for me, is taking a look at the experimental comparisons. So what we're going to do is look at all the tests that have been conducted, and some of them were in that original University of Texas report, and I believe some were done overseas somewhere. I can't quite remember where, and then I think some were also done at the University of Alberta. So we ended up, I was kind of surprised to see that there were 18 specimens that failed at the cope in some sort of either shear or stability, local stability, or yielding. And using the design procedure, we ended up, I don't want to bore you with all the numbers, we'll look at the figure next, but the experimental to calculated ratio using that design procedure in the manual, this is all nominal, is 1.23. And the standard deviation is fairly large if you're thinking about designing a beam or a tension member or something like that. But for connections, the 0.268 is pretty reasonable. So you can think of this number, the 1.23, as being on the conservative side if you want, but to know that for sure, that's just kind of how my mind thinks. If it's bigger than 1, it's on the conservative side. But you've got some reliability things in there that there's really not enough specimens to do a full reliability study. Now this figure is going to give you the real picture of what the test results are doing. The red on the right-hand side are the elastic buckling, and the darker squares, I believe they're blue-colored, are inelastic buckling. And you can see on the horizontal axis, you've got a normalized slenderness. There's the values for the 0.475 in lambda sub p, and that's the one, that's 2 times lambda sub p here. So that's the normalized slenderness. And up here on the vertical axis, we have M over MP. So it's kind of a normalized moment. And one interesting thing is that none of the specimens failed in the plastic range. and none of the specimens were predicted to fail in the plastic range. So that's always good. It looks like we predicted that fairly well, but of course, we use the specimens to define lambda sub p, so you would expect it to match up in that regard to the specimens pretty well. We did have this one specimen that failed inelastically in the test, but we predicted elastic buckling since it's in this range, but there's not much we can do about that. It's way over there with all those other red specimens. I don't know what it's doing over there. All right, so I think that pretty much tells the story. The old way we had it, we had this elastic curve, and then we were cut off at the section modulus. So we were probably way down here with the horizontal curve, and then it went to the elastic curve, is what's in the 14th edition. So we were using the elastic yield moment or the elastic buckling moment. So you can see that especially for these, which are the most common cope sizes, you're getting a significant increase. Oh, I forgot to tell you about the midterm exam. The pop quiz on the single coat beams. Now we're going to have a final too. It'll be on double coat beams, so make sure you pay attention. I'll give you a hint on the question for double coat beams. It's the same question as for single, and the answer is the same too. At least the three selections, A, B, and C, are the same. The answer may or may not be different. Okay, so the design model for flexural strength of a single coat beam is based on A, B, or C. Flexural buckling, which is out of chapter E, that's a column type buckling. So I don't know if I've got any takers on that or not. B is going to be lateral torsional buckling out of chapter F, kind of a beam type buckling. And of course, at the very bottom, we end up with the local buckling. So I think that, does anybody need a hint on this? I think we can go ahead and take the top one out because it's not a column, right? All right, if anybody wants to take a wild guess on B or C. You're going C? All right. That's 100 points. All right, well, I think so we can probably eliminate, well, I don't want to give any hints or anything, but we might be able to eliminate C for the final exam. But here's the thing, is that we really need that information. It was kind of a good review for what we need coming up, talking about the judgment type thing. You know, we need to be able to use our judgment. How do these things fail? And we know that in the past, the Euro report and several others now that have been published after that, the design model was based on a local buckling model for flexure. All right, so then we go put this beam in compression, this cope in compression. How do you think it's going to fail? I mean, we can all use our own judgment, but in my judgment, I think that it's going to fail in a local buckling mode because that bottom flange is strong enough and stiff enough to brace the web at that location, and maybe you'll get no or negligible deformation near that bottom flange, and all of your deformation, like a plate buckling problem, you would have near that top part where the flange is cut out. But before we get to that, we get to talk about something easier, something that's in the spec. It's the tension strength. So we need to talk about the tension strength and then the compression strength of these. The tension strength is just defined in chapter J 4.1. It tells you to design it just like any other tension member. So you're taking the area at the cope, though. You know, of course, your area is going to be this reduced area at the cope. Take that gross area times the yield stress, and that's what the specification tells you to do, and we're finished. Throw a fee factor on there or a safety factor if you're ASD. Don't forget about that part. Now for the compression strength. Now this is where I started kind of using some judgment here. And I went into spec section E7. That's for slender members. It's for local buckling of slender members. And the equation looks the same. The compression strength is the yield stress times A sub E instead of A sub G, because E is the effective area. A sub E is the effective area rather than the gross area. And if you're familiar with cold pour and steel design, you'll be able to jump right in on this, because what happens is for a slender web, which most of them are, unless you have a jumbo shape or something, it basically cuts off a portion of that web from here to here, say, and uses the area from there down. So it's an effective area under compression. So A sub E equals A sub G when lambda is less than or equal to lambda sub R. But that's hardly ever going to happen for copes. Usually they're going to be down here in this second range. One thing to note is that we're redefining lambda sub R for axial. It's the same as what you have in chapter B. You know, if you've got a beam, your beam would have different slenderness requirements than a column. So for axial load, our lambda sub R has the same form. It's some constant with the square root of E over F sub Y, and we've got a K in there, but I've called it K sub A for axial. You know, it's kind of hard to keep up. We've had, I think, 3 different Ks now. So I call this one K sub A. And when you go into that E7 and start looking around at the way things, it looks a little different from the way the specifications looked in the past. But after I started looking at it, it's you can come up with some pretty simple formulas using that. And after I plugged everything in, this is not in the spec, this part isn't, but I used the specification to come up with this equation. So if you could probably come up with the derivation of this just by going into spec section E7. All right, so you end up with this pretty simple equation. It's got A sub G minus some value out here, and that value is dependent on lambda sub R, which we know how to calculate from over here, and it's dependent on lambda. That hasn't changed. That's still H sub O over T sub W, and we've got the web thickness in there, which we know what that is. So the only thing that we're missing now is the same as what we had before, is this K sub A. We don't know what that is. So let's take a look at what we did for that. As it turns out, this K sub A can be based on an infinite cope length, or say a WT, when this cope to H sub O, the cope length C to H sub O ratio is greater than or equal to 1.64. So for long copes, you're not going to get any support, any out-of-plane support to brace that plate and increase the strength. So you use a K sub A equals 1.28. And if you just want to be conservative all the time, you can always use 1.28. If you want a higher number to increase your cope strength, you can go down here. When C over H sub O is less than or equal, or is less than 1.64, your K sub A is given by this, which is only dependent on this ratio, C over H sub O, and then it's turned upside down over here. We know what C is. It's the cope length. So with all of that, we know what the flexural strength is, we know what the axial strength is, and we know what the shear strength is. So how do we combine all of these? And this is another thing that fairly recently, for both single and double coat beams, we have test results for. And I think most of these, if not all, were done at the University of Alberta. Dr. Driver and his group up at the Steel Center up there are doing a lot of good work on connections. So I took a look at the testing, and as it turns out, it was a little too conservative to try to combine all 3 of those loads. You know, load ratio, like an interaction type equation with all 3 of those things in it. And I found out after looking at the tests that really the longer copes failed in an axial flexure. The longer copes that were subjected to axial loads, axial compression loads, failed in axial flexure interaction. And the shorter copes failed in axial shear interaction. So that gives us a reason to simplify this thing. For axial plus flexure, all we have to do is calculate this ratio, where this is our axial load ratio. This is all in lrfd. For ASD, it's going to be similar, but you're going to, of course, do away with the phi factor and put your omega up here. And you add the moment ratio to that to get a linear interaction less than or equal to 1, and you're done. On the other hand, if you have axial shear interaction, as it turns out, if you have tension only on your cope, now most of the time we're going to have reversible loads where you have tension or compression, but I wanted to separate this because if you have tension only, there's no interaction required. It kind of stabilizes the web. So it kind of helps you a little rather than hurts. So axial tension plus the shear load, there's no interaction required. And the primary case where I think this would come in handy is where you have those giant structural integrity type loads where you're required to put a certain percentage of the gravity load onto the end of the beam and an axial. So that might help you in those cases. Otherwise, if you're in compression or have reversible loads, you need to do this linear interaction of axial strength ratio plus shear strength ratio less than or equal to 1. Now, the best thing to do, I couldn't figure out where the cutoff point was, where one interaction equation, the axial shear or the axial flexure happened. And I didn't really make too much of an effort because it's just as easy to calculate both. We've got all the numbers. All we have to do is run it through the linear interaction and we're done. Run it through both of them and whichever one controls, let that be your design. All right, let's move on to the double coped. Now that we've got the single coped pretty much nailed down. We're going to do the same thing for double coped as we did single coped. Shear, flexure, axial, and combined loads. For the shear strength, all I did with this slide is I copied that slide from the single copes and I changed the picture to a double cope. It's the same equation, same part of the specification, shear yielding along this plane. The only difference is the H sub O is now defined as it's still the remaining depth, but you have to subtract out the top and the bottom cope from D to get H sub O now. So most of our time, the time we have left really is going to be based on, is going to be in this background for double cope beams for flexure. And this is also coming from the Ching-Yura and Johnson report, University of Texas. If you look at these, the way they buckle, these double cope beams, you really can't tell from this buckled shape that I've got up here, but if you cut a section straight through the worst part here and show the side view, the section through that, there's the non-buckled shape on the left, and you can see that you have, if you look at the centroid, you're going to have lateral translation and twisting of the cross-section, which is a traditional lateral torsional buckling failure. One other thing that I'll note is that if you look really close at the deformed shape here, there is some distortion in that web. In other words, there's some bending. There's a thing called distortional buckling that it happens in every beam that we've got. Every wide flange beam has distortional buckling in there that lowers the strength. It's just that it's negligible. I mean, in a wide flange beam, the dimensions are so that the the distortion is imperceptible. So you get a negligible reduction due to distortional buckling for normal lateral torsional buckling design. Now in this case, it might be enough to where we have to do some type of fudge factor again, on top of our lateral torsional buckling model, but we have to start somewhere. We have to start with a model somewhere, and we're going to start with a cantilever beam, just like we did with the single copes, and then we're going to do lateral torsional buckling model, just going off the work of Ura, and then verifying with mine and Robert White's finite element models. And we're going to basically just extend his work using these finite element models. As it turns out, sometime between the Green Book, I don't know when it happened, the Green Book and the 2016 specification, section F11 was added to the specification that handles rectangular cantilever beams. So we have something built into the specification that allows us to calculate the buckling strength of a rectangular beam and account for the inelastic effects and the geometric imperfections and all those things that we don't really have to worry about in this research. It allows us to account for all of that. Residual stresses, all the things that kind of affect the buckling strength, especially in the inelastic range, we're not going to have to worry about. So these models I'm about to show you are all done elastically using the same program that was developed at the University of Texas. Professor Ura was nice enough to send me a copy back when we were doing this research. So what we're going to do in the manual is go to spec section F11, but spec section F11 requires us to define what L sub B is, which is the length of beam between brace points, and it requires a C sub B value, unless you want to just say C sub B equals 1. That's probably okay in a lot of cases, but for these, our C sub B values are going to be pretty big in some cases. So you probably want to go ahead and calculate C sub B greater than 1 before you go into the specification. So what we're going to do, the first thing we're going to do is go to the manual, calculate L sub B and C sub B, and then we're going to go into the spec and calculate from spec section F11 what the strength is based on that L sub B and C sub B. So the L sub B and C sub B were developed by me and Robert in a paper published. When was that, Robert? Maybe 5 years ago or something? So 5 years ago, which the heavy lifting was done by Robert. We need to drag him up here and get him to present this part, I think. But he can probably explain this a lot better than I can. He did most of the finite element modeling and came up with a lot of great ideas for this. But here's what we started off with. First of all, we had to label this D sub CT, because before it was D sub C for cope depth. Now we can have different depths at the top and the bottom. So we got D sub CT and D sub CB. So we took D sub CT over D, where D is the depth of the member, plotted that on the horizontal, plotted C sub B, that's used in spec section F11 on the vertical, and plotted all the finite element models, the results of the finite element models. There's not a huge difference in this figure, but the next one, where we did the same thing, but this time we took C sub T, the cope length at the top, divided by D, and plotted it here, and C sub B is still on the vertical. We ended up with a dramatic change as we increased C sub T over D. Our C sub B went up dramatically, especially, and this range, it's not really going to buckle in this range anyway, because that cope length is too short. But once we get up to where it will buckle, we ended up with these curves, and we based our equations that I'll show you on those curves. But first, let's take a step back. We look at all those figures and things like that about the data, and we talk about the equations, but really just kind of a common sense type thing. Let's take a look at what's going on here. This top one, that's a kind of what you would think of as the base case. It's got equal copes at the top and the bottom. And you can see how it buckled out at the top, and then you can't see the part, but it's kind of dragging that tension edge along a little bit for the ride, and you get some lateral translation and torsion. And then we decided, well, what happens if you shorten the bottom cope and leave the top cope the same? And now you're comparing these two. And the buckle shapes really, I mean, they're just not that much different. You know, it had a little more strength, but not much. And then let's go in the opposite direction and increase that bottom cope. You end up down here, so now let's compare these. And really, we can compare all three at this point. They're all almost identical. The load's just not that much affected by the bottom flange. And you can tell by the buckle shape. So let's take a look at what's in Manual Part 9 for the double coat beams. We already know this part, but don't forget about E. The lower justification, lower value can be justified for E is also in this part. In fact, I think it's just one at the very beginning for double cope and single cope for defining E. Okay, spec section F11. I'm not going to go through all these numbers, but the main thing I wanted you to know is these are what the equations look like. You can think of this as lambda if you want, and lambda sub p here. One thing to notice, 0.08, that's a tiny number. The plateau, the plastic plateau, that horizontal line for these beams is just, it's tiny. The 0.08, I mean, you'll hardly ever get there this way. You can get there, but you can get to the plastic strength, just not this way, not by being this ratio less than this ratio. The main thing that I wanted to point out on this slide is that L sub B is the distance between brace points in the specification. All right, we're going to have to define that. That's defined in the manual. D, all right, that's the rectangular cantilever beam depth. In our case, we need to substitute H sub O. Before we go into the spec, H sub O equals D. And we've got T on the bottom down here. And of course, that's going to be the thickness of a rectangular cantilever beam, which is equal to T sub W, or the web thickness. So we need to use those values to go into the spec. Now, this is where you're going to be a lot of the time with your you'll be in the next two zones. You'll be in this inelastic transition zone or the elastic zone. But here's the thing, C sub B, you've got C sub B over here, and of course, just like any other specification requirement, it can be no greater than M sub P, the plastic moment. So that makes sense. But a lot of times C sub B, in our case, is going to be so big that you can get the plastic moment out of the design being within this geometric range. All right, so that's the linear transition, the inelastic transition part of the curve, but a lot of times you'll end up on that plastic plateau, that straight line. And the same thing in the elastic range. You end up with, these are straight out of the specification, you end up with F critical times S net less than or equal to MP, and here's our F critical equation. It's got all these things down here that we just defined, but we still need to know what L sub B and C sub B are. And to get those values, we go straight to the manual. And these are the equations that Robert and I worked on. And you can kind of, it's a dead giveaway that you've got a natural log in there. We tried to figure out how to eliminate that just so it wouldn't look so goofy. But it's a dead giveaway that it's an empirical type or based on the finite element models. So there's your C sub B equation. It's dependent on L sub B, which we define up here, depth of the beam and the depth of the top cope. And one thing I'll point out here is that that's greater than or equal to 1.84. The manual, I believe even the current manual says less than or equal to 1.84. And I'll take credit for that because that's a mistake. And that's a mistake that's also in our journal paper that was published in the AISC Engineering Journal. It should have been greater than or equal to 1.84 rather than less than or equal to. Okay, so there's your equation for C sub B, and here's your equation for the cope length. This is all for the cope length, for equal cope lengths at the top and bottom, or C sub T less than C sub B. So this is where you'll be most of the time, with equal cope lengths. So this makes sense that our buckling length is going to be equal to the top cope length after those buckle shapes that I just showed you earlier, that it's not really dependent too much on the bottom cope. So in case that you do have C sub T, the top cope length greater than the bottom cope length, you can go to this equation where L sub B is defined as the average of the top and bottom cope lengths. And then this equation for C sub B is the same as what we had before in this part, but then all you have to do is multiply by the ratio C sub B over C sub T before you go into the spec. So we tried to get good, despite that L sub, that natural log, we tried to get good simplified equations for you. And it looks like we're on time. So you know, Jules, the best way to throw off the timing of a presentation is to start telling stories. So I think I'm going to throw off the timing of this presentation by telling you really, I mean, that looks simple enough. So the L sub B equals the average of the top and bottom cope lengths. So it's, you know, a kindergartner could have made that up, right? Maybe second grader, just average of the top and bottom. So why is it so simple? And the answer that I'm going to give you is because that's what the finite element models say. And of course, you know, these two work together. L sub B and C sub B work together. So we could have adjusted some things in C sub B if we wanted to, if we're defining L sub B a certain way. But the story is this. That equation, I didn't make that equation up, and Robert didn't make that equation up. That equation was made up by Professor Ura, and I bet he doesn't even remember it, because my business partner at the time, 20 years ago, Martin Coffey, we were sitting in a little, it was a two-man engineering outfit, and I think we had been in business for about 3 days, and we didn't even have cubicle walls, but we did have Professor Ura's report. And so he was flipping through this report. He had a double coat beam that had different coat sizes at the top and bottom. And he said, you know, I don't know what to do about this because all these equations are based on equal coat depths. And I'm concerned about this. I'm going to try and figure out what to do. So he said, I'm going to call Dr. Ura up. And I started thinking, well, he's too busy deriving equations on column buckling, and which, by the way, he's got a really good presentation at this one. I haven't been to it yet, but he's got a good presentation on the history of column buckling at this conference that I want to go to. So he's too busy deriving column buckling equations and coat buckling equations and things like that to answer some silly question from a connection designer sitting in an office trying to design one connection on a project. And being that we had no cube walls, I could hear everything that was going on. You know, he was on the phone. This is back when we had to actually, I don't know how he got his number. You know, we had to use phone books back then. So he calls Professor Ura, and he answers, to my surprise. And they're over there talking like best buddies, and 5 minutes later, he gets off the phone, and I said, well, what did he say? And Martin said, he said that he thought about it for a minute, and he said, I don't know, what the heck, why don't you just average the two? So that's where that equation came from. We're averaging the two, but we've verified it with finite element models 2 decades later. But the point that I'm really trying to make here is going back to that judgment thing. You know, we've modeled these things as cantilever beams. And we're modeling it with a lateral torsional buckling model. And Professor Ura knew how they behaved because he had the finite element models for this report. And he used that knowledge of the way they behave to give an estimate. And as it turns out, I mean, I'm always amazed that he can come up with these simple rules, him and other people like Professor, or like Dr. Thornton, Bill Thornton, for gusset plates and things like that. They can come up with these simple rules, and it's not just based on saying, oh, what the heck, why don't you average the two? It's based on thinking about it and knowing what the failure mode is. So that's the point I'm trying to get. If you know how it's going to fail, you can come up with a good design model. And that goes for copes or anything, any type of connection element. All right, we'll try and catch up now. I don't think we're too far behind. Experimental specimens, experimental comparisons, 24 specimens. I was shocked to find 24 specimens. I can't even remember where they all came from. I know Alberta did some, and there were no actual test specimens in the original report. So we ended up with what I would think of as a conservative average experimental to calculated ratio using the nominal strength of 1.6. But the standard deviation was pretty high, and we ended up with a minimum experimental to calculated of 0.924, which is greater than the phi factor. So just kind of in my world, just kind of the simple guy world, without doing there's not enough specimens to do a full-blown analysis of the data to find out what our phi factor should be. So it looks pretty good to me, 0.924 is greater than 0.9, which is our phi factor for bending. And the picture doesn't really paint a good picture either, because even over in, well, the one thing that it does do is that all the red dots are on the right part of the curve, and all of the blue squares are on the left side. They're on the plastic plateau, so it predicts the proper failure mode. And over here, there's nothing we can do about all these, at least to my knowledge, because it's probably based on what we're, our M over MP, which is on the vertical. That's our slenderness, again, our normalized slenderness on the horizontal. These up here that are 1.5, so that's 50% conservative for those. So you get things like that we really can't account for. We've already said it's going to equal the plastic moment capacity of that beam. So you get strain hardening. And another thing that we might need to look into is that could potentially also be due to the inflection point moving out toward the cope from the face of the support to the cope. So that might be where one of these are conservative in this range. Now, as for this part, it looks pretty good in this range, but then it starts getting conservative again in this for these that are really slender. Most of our specimens are going to be in here anyway, but for these, well, you might say, well, why didn't you just make that curve go right here? And we could have done that. We could have, we could do it. But the problem is that these specimens, all of these specimens out here, none of those had the imperfections measured. So we didn't have the out of flatness of that web. We didn't have the initial twist, which is something that you need to look at for lateral torsional buckling, and we didn't have the residual stresses. So what if these are all perfect? We don't know. They may have been almost perfectly straight, perfectly flat, and then we come along and design something that you might do some welding on to cause some distortion, or maybe it gets bumped in shipping, or maybe it's just out of flat from cutting the cope, by 1/16 of an inch or so. Well, I mean, I'm not comfortable moving this curve up just yet until we get some more information there. I mean, it's kind of up to you if you want to, but this is going to be what's in the manual, and you can kind of use your judgment. All right, the final exam. It's the same question we had before, except for this time we're talking about double copes. Design model for the flexural strength of double coat beams is based on I've already given it away that that's column buckling, right? So that's probably not going to be it. We can go ahead and mark that one off. So we're left down to these two, and I think that I've talked about it enough where everybody knows which one to go with here. All right. Looks like that's right. All right. So once again, we're going to use that info, though. We're not quite to the end yet because we still have to talk about axial strength. We're going to use that info to go in and calculate axial strength. Now, to combine with lateral torsional buckling, if you think of member design, say you have a W16 spanning 30 feet, and you want to calculate the compression strength plus the flexural strength combined, you would probably go, just straight to the spec, combine per chapter H, which is similar to what we've done, and then go to chapter F for the lateral torsional buckling, which is what we've done. We've gone to F11, and then for the compression, you would go to chapter E. All right, but as it turns out, that the tension is the same as what we had for single coats, section J 4.1 of the specification. For compression, we can go to chapter J, which is for connections, J 4.4, and let's see what that gives us. That's going to be a flexural buckling. It's going to be the same as what we have in chapter E for flexural buckling of a column. And the way to tell, at least in my mind, the way to tell if you should be using this part of the specification to calculate buckling, because we didn't do it for single coats, why would we do it here? Well, here's the reason, is because take a look at the buckle shape, what you think the buckle shape would be for this member, for this cope, and if that point and that point translate out of the page equally, then that's going to be a flexural buckling. So it's going to be a column type buckling, if you want to think of it like that. So that's what we're going to do. We're going to use column buckling per specification chapter J 4.4. And we're not going to go through all the equations, but I will just tell you that if your slenderness ratio KL over R is less than or equal to 25, it allows you to use the tension yield strength with no reduction for compression. And then if the slenderness ratio KL over R is greater than 25, it sends you to chapter E of the specification and tells you to design as a column. Now, what I will say about this is, the judgment thing again. What do you use for K? I mean, I think L is pretty well defined here as E or maybe C, which kind of goes to the braced location back here. So, so L is pretty well defined, and R is defined. It's just the web thickness over the square root of 12. But K is the big deal that we need to come up with. And of course, it's, I can't give you a number. Typically, I would use 0.5 in that case, the theoretical value. But that's only for, like, if you have a 16-26, a quarter-inch thick web, and then you've got 5/16 clip angles, double clip angle connection on there to restrain that end, on this end, then I would, and let's say that's braced by decking up here so it can translate, then, yeah, I would use K equals 0.5. But what if you have a jumbo shape with a 3.5-inch thick web and 3/8-inch thick clip angles, and that's not braced up here? Then I'm not sure what to use. You would, I would assume no restraint, no bending restraint here in that case, I don't think. Using 3/8 clip angles, I don't think you could brace that web. So that, it's up to you to determine. If it's buckling in sway mode, you might want to think about using the sway buckling factors, the 1.2 or something like that, or maybe even 2. Okay, finally, we're going to do the combined loads on this, and it's identical to what we did for top coat. The double coat will be, I noticed kind of the same things when I was looking at these tests, where it was broken down into the short copes and the long copes, where you get the two different types of interaction, axial flexure and axial shear. And there's your straight line interaction. It's the same as what we had up there for single copes. For tension, there's no need to interact axial and shear. And for compression, axial and shear get the same treatment as for single copes, which means straight line interaction. I was thinking we had another quiz up here, but I guess this is it. All right, so what we've talked about, though, is how we went from an elastic-based allowable stress design to a strength-based philosophy from the 14th edition to the 15th edition manual, where we get to take account of any inelastic or potentially plastic strength of the copes. There are no longer any limits on the cope geometry. You can do whatever you want. If you have super long copes, though, think about that lateral torsional buckling of your beam, of the overall beam, you know, because those connections aren't going to be able to restrain it the way it would, your equations say that the beams are pinned at the end, that they're supported at the end for rotation, and that's not going to quite give it to you. That long connection that I showed you in the third slide, I believe. So the design model, local buckling for top coped and lateral torsional buckling for double coped. And I believe do we have time for questions?
10 minutes.
Okay. 10 minutes for questions. Okay, yes.
Yes, on your final element model, you have a size for the mesh, and you do a mesh sensitivity study to determine whether you're actually using the most appropriate mesh size?
No, the meshing is all done. I don't even know if the program is available anymore. The program is called BASP that we used. It was developed at the University of Texas, and it sizes the mesh for you. That's one of the main reasons we used it, is it does all the meshing for you. We didn't even, I mean, each of these models is almost built automatically for you. We just had to build the beam and cope it out, and it meshed everything for us. So no, we didn't do a mesh study at all, and nor did the original research. The question was about the mesh size. I forgot to repeat the question. Okay, yes.
You have a paper that you just put out about plate elements and interaction between shear, flexure, compression, all of that. What's the difference between that kind of interaction and the interaction with just simple linear interaction, just on the coped elements here? Because that seems to me like a double cope, especially, it's a plate element compared to just a single plate somewhere.
Yeah, that's right. And there is a difference. The question was whether this interaction, why is this interaction not the same as what was published in a paper? The paper was called, I believe, now you're referring to the plastic strength of rectangular connection elements paper. Okay, there's a paper in the engineering journal that was published sometime in the last 3 years or so, titled Plastic Strength of Rectangular Connection Elements. And in this case, for the rectangular connection elements, it would only apply to the double coped. So the interaction equations developed in that were for rectangular cross sections only. And the reason that they're different, if you look in that paper, it goes through and gives you an equation for the plastic strength under any combination of loads. But the problem is here, we have an interaction on stability, not an interaction on the plastic strength. So if you can get this, if you can somehow get this double coat beam to behave plastically. In other words, you would make your K over R less than 25 so that you don't have stability effects and compression, and then you would have to be on that horizontal plateau where your moment's equal to MP, and that's a pretty high bar. But if you did that, then you could use the plastic interaction equations, which have the ratios are raised to powers, so you get more strength out of it. Essentially, is what it does. The axial strength ratio is squared, I believe, in those equations, and the flexural strength, M over MP, is to the first power. And then if you calculate the shear strength and add it to that too, it's raised to the fourth power for the plastic strength. But you can't use that with stability effects. In fact, I believe there's a paper that's either already been published or it's about to be published on stability of rectangular connection elements. And that goes through and explains where you can and can't use those plastic interaction equations, and then it gives you alternative equations when stability does come into play. And it complies with this too, because it gives a straight line interaction when stability is critical for both the moment and the axial. Okay, any more questions?
Actually, here, I have one off here. It says, in the case where a double clip angle is welded to both sides of the cope beam web for approximately the full depth of the uncoped section, will the welded angle legs provide significant lateral restraint to the relatively thin web? And if so, can this be considered to add strength to the cope section? It's referring to double cope beams failing laterally along the compression edge.
Okay, yeah. The question, I don't know if you heard the question or not, but the question is can clip angles be used to stabilize the web? And my answer is, I mean, yes, they do stabilize the web, but I don't know how to calculate it. So the problem is that if you can come up with a way to calculate it or estimate the effect, then you can use the clip angles to stabilize the web. In fact, I mean, if they're take an extreme example and say that the clip angle length, and we have had this before, where we've used our judgment on real structures where the clip angle length, it's got a giant axial load on it, so we had to use 8-inch clip angle legs, for example, and then maybe we might have a 6-inch cope. So the clip angles extend beyond the cope. And in that case, well, if you've got, say, a 3/8 web and 3/4-inch thick clip angles, you know, I'm not going to go through and calculate all of these buckling equations. I'll just use my judgment and say, we know that this is not going to buckle. Okay, any more over here?
No, it's all good over here.
Okay. All right. It sounds like we're ready to go out here too.
Thank you, Bob.
All right.